Assalamualaikum everyone. Today I'm going to explain chapter 3, which is chemical bond. So what is chemical bond? Chemical bond is a strong attractive force that exists between atoms in a substance. Next, there are three types of chemical bonding, which is ionic bond, covalent, and dative covalent bond. Next, the definition of ionic bond. Ionic bond is the electrostatic force of attraction between positive ion, cation, and negative ion, anion. Then, covalent bond. Covalent bond is a chemical bond in which two or more electrons are shared by two atoms. And lastly, dative covalent bond. Dative covalent bond is a covalent bond, a shared pair of electrons in which both electrons come from the same atom.
First, ionic bond. Here are the examples for formation of ionic compound. As we can see, sodium Na has 1 valence electron, while chlorine Cl has 7 valence electrons. After the formation, sodium becomes Na plus because it loses 1 electron, and chlorine becomes Cl minus after gaining 1 electron. Next, covalent bond. Covalent bond has three types of bond, which is single bond, double bond, and triple bond. For decreasing strength, triple bond are the stronger, meanwhile single bond are the weakest. Next, covalent bond. Each fluorine atom has 7 valence electrons and need 1 more electron to achieve a stable octet. When two fluorine comes together, each atom shares 1 electron and with the other, forming one shared pair of electrons. This sharing creates a single covalent bond between the two fluorine atoms, allowing both of them to achieve an octet electron configuration and form the F2 molecule. Next, type of electron pair in covalent bond. In covalent bond, we have two pairs, which is lone pair and bonding pair. What is lone pair? Lone pair is a pair of electrons that belongs to a single atom only and does not participate in bonding. Next, what is bonding pair? Bonding pair is a pair of electrons shared between two atoms to form a covalent bond. Last is dative covalent bond. Here are the examples for dative covalent bond. As we can see, the nitrogen atom in ammonia has a lone pair of electrons, while the hydrogen ion from hydrochloric acid has no electrons to share. So, nitrogen donates its lone pair to the hydrogen ion, forming a dative covalent bond and producing the ammonium ion NH4+, while the chloride ion Cl- remains separate.
So now, we're going to move on to our next topic, which is drawing Lewis structure. So for an example, Lewis structure of ammonia. First, we calculate the total number of valent electrons. Nitrogen has 5 valent electrons and each hydrogen has 1 valent electron. Since there are 3 hydrogen atoms, so 5 plus 1 plus 1 plus 1 equal to 8 valent electrons. Step 2, we arrange the atom. Nitrogen is chosen as the central atom because it is more electronegative than hydrogen. Hydrogen can never be the central atom. Each hydrogen forms one single bond with nitrogen. Each bond uses 2 electrons. We have 3 bonds, so 3 times 2 equal to 6 electrons. Step 3, determine non-bonding lone pair electron. We started with 8 valent electrons. After forming 3 bonds, which we have 6 electrons, the remaining electrons are 8 minus 6 equal to 2 electrons. These 2 electrons form one lone pair on the nitrogen atom. So, the Lewis structure of ammonia has 3 single bonds between nitrogen and hydrogen and 1 lone pair of electron on nitrogen.
This image introduces the VSEPR model, which stands for Valence Shell Electron Pair Repulsion. It explains that a molecule shape is determined by the repulsion between electron pair around a central atom. The notation ABL shows a central atom A bonded to surrounding atoms B, where X represents the number of bonds, depending on whether there are lone pair or no lone pair on the central atoms. the molecule shape can change. VSEPR helps us predict the geometry of molecules. This image shows the main molecular shapes predicted by VSEPR theory, which explains how electron pairs arrange themselves to minimize repulsion. Linear molecules have atoms in a straight line. Trigonal planar molecules have 3 bonds arranged flat in a triangle. Tetrahedral molecules have 4 bonds pointing to the corner of a pyramid. Trigonal bipyramidal molecules have 5 bonds arranged in 2 different positions, equatorial and axial. Octahedral molecules have 6 bonds evenly spaced around the central atom. These shapes help us predict molecular geometry, bond angles, and polarity. This image explains how lone pairs on the central atom affect molecular shape using the VSEPR model. Lone pairs repel more strongly than bonding pairs, so the order of repulsion is lone pair/lone pair is greater than lone pair/bonding pair, which is greater than bonding pair/bonding pair. The notation ABXEY shows a central atom bonded to X atoms with Y lone pair. Because of lone pair repulsion, bond angles become smaller, as seen in molecules like NH3 and H2O. This is why molecules with lone pairs have distorted shapes compared to ideal geometries. This image shows several molecular shapes based on the VSEPR theory. Bend shape occurs when the central atom has lone pairs that push bonded atoms closer together. Trigonal pyramidal shapes forms when there are 3 bonded atoms and 1 lone pair, giving a pyramid-like structure. Distorted tetrahedral or seesaw shapes happens when low pairs distort the ideal tetrahedral arrangement. These shapes affect the molecule's polarity and chemical properties. This image explains the geometry of molecules with more than one central atom. Instead of describing the shape of the whole molecule, it is more accurate to describe the geometry around each central atom. In this example, the first carbon atom has a tetrahedral geometry. The second carbon atom is trigonal planar, and the oxygen atom bonded to hydrogen has a bend shape. This approach helps us understand how different parts of large molecules react at specific sites. This image shows a dipole moment in a polar molecule, using hydrogen fluoride as an example. Fluorine is more electronegative than hydrogen, so it pulls the shared electrons closer to itself. As a result, the fluorine side becomes electron-rich and slightly negative, while the hydrogen sides become electron-poor and slightly positive. This uneven distribution of charge creates a dipole, which makes the molecule polar. This image explains the polarity of molecules by comparing polar and non-polar molecules. A polar molecule is made of different atoms and has an unequal sharing of electrons, which creates a dipole moment. A non-polar molecule either contains identical atoms or has a shape where bond dipole cancel out. Overall, molecule polarity depends on both the polarity of the bonds and the shape of the molecule. This image compares the polarity of CO2, H2O, and NH3 by showing their bond dipole and overall dipole moments. In CO2, the molecule is linear, so the bond dipoles are equal and opposite. cancelling each other out, making it non-polar. In H2O, the molecule is bent, so the bond dipoles do not cancel, creating an overall dipole moment, making it polar. In NH3, the trigonal pyramidal shape also causes the bond dipoles to add up, resulting in a polar molecule. This shows how molecule shape affects polarity, not just bond polarity.
Today, I will explain about intermolecular forces. Intermolecular forces are the forces of attraction between molecules. There are two main types of forces, intermolecular forces and intramolecular forces. Intermolecular forces are forces between molecules. They influence the physical properties of substance such as boiling point, melting point, and solubility. These forces are weaker than intramolecular forces. Intramolecular forces are forces within a molecule. They hold atoms together by chemical bonds such as covalent or ionic bonds. These forces are strong and affect the chemical structure of a substance. For example, hydrogen bonding is a type of intermolecular force. It occurs when hydrogen is bonded to highly electronegative atoms such as oxygen or nitrogen. Intermolecular forces can be divided into two main groups, van der Waals forces and hydrogen bonding. Van der Waals forces consist of three types: ion dipole forces, dipole-dipole forces, and London dispersion forces. Hydrogen bonding is a strong type of dipole-dipole force. It occurs when hydrogen is bonded to highly electronegative atoms such as oxygen, nitrogen, or fluorine.